Chapter 18 Acid-Base Equilibria. In this chapter, we'll study the following topics: the definition of acid and base in different theories, Arrhenius theory, Bronsted-Lurey theory, Lewis acid-base theory, the conjugate acid-base pairs, pH, pOH, pKw, examples of strong acid, strong bases and their properties, weak acids and bases, pKa, Ka, Kb, calculations involving weak acids and polyprotic acids, calculations involving weak bases, acid-base properties of salt solution. The Arrhenius acid-base definition is the earliest acid-base definition, which classifies these substances in terms of their behavior in water. In this theory, an acid is a substance with hydrogen in its formula that dissociates to yield hydrogen ion. So hydrogen becomes hydrogen ion. In water, there's lots of water molecules, H2O. The hydrogen ion that dissociated from acid combine with water to form H3O plus called hydronium ion. So it is more precisely to say acid dissociate to yield hydronium ion in water. Note that an acid is not just a substance with hydrogen in its formula. It must be able to dissociate to yield hydronium ion in water. For example, methane, as we learned in the last chapter, is the smallest organic molecule. Although the molecule contains hydrogen, the bond between carbon and hydrogen is too strong to break, and therefore it cannot dissociate to hydrogen ion, and therefore it's not an acid. On the other hand, hydrogen chloride can easily dissociate into hydrogen ion and chloride ion, and therefore, according to Arrhenius theory, this is an acid. Hydrogen chloride is a Arrhenius acid. A base is a substance with hydroxide in its formula that dissociates to yield hydroxide. For example, sodium hydroxide. Okay, it's a base because it can dissociate into sodium ion and hydroxide ion. Okay, when an acid reacts with base, they undergo a reaction called neutralization, and the reaction is like this. In water, for example, hydrogen chloride, as we shown here, dissociate into hydrogen ion, chloride ion, and sodium hydroxide dissociates into sodium ion, hydroxide ion. Okay, in the solution, these ions floating around, and when hydrogen ion meets hydroxide ion, they combine together, give a water molecule. Chloride ion remains as chloride ion. Sodium ion remains as a sodium ion. They do not change, and they are called spectator ions. So what really happened is hydrogen ion, hydroxide ion forms water. So we have a net ionic reaction equation shows that the neutralization between an acid and a base in Arrhenius theory is hydrogen ion, hydroxide ion forms water, and this reaction releases large amount of heat. Acids have the following properties. They react with metals. For example, when magnesium is placed inside hydrochloric acid, and you can see bubbles coming out of the solution, and this is due to the hydrogen gas formation. Acids taste sour. Lemon tastes sour because citric acid and organic acid inside lemons. They react with the base, as you already seen in the last slide, to form water and a salt. Acids turn blue litmus paper into red. This is an indication that existence of acids. This table lists some common laboratory acids. Their molecules all contain hydrogen to donate. Hydrochloric acid, is HCl, is used for cleaning of metals, preparation of foods, refining of oils. Sulfuric acid, H2SO4, nitric acid, HNO3, are both used for manufacturing of fertilizers, explosives, dyes, and glue. Phosphoric acid, H3PO4, is used for manufacture of fertilizers and detergent, flavored additive for food and drinks. Acetic acid, CH3COOH, also called vinegar, can be used in manufacturing of plastic and rubber, used as preservatives in foods, etc. Bases have the following properties. They feel slippery and they taste bitter due to hydroxide. They react with acid to form water and a salt. They turn red litmus paper into blue instead of red. Bases are found in many cleaning products as shown here, and they burn skin and damage gastrointestinal tract on contact. This table lists some common laboratory bases: sodium hydroxide, potassium hydroxide, sodium bicarbonate, and ammonia. What is a strong acid? Since acid is defined as a substance that can donate hydrogen ion or hydrogen ion in water, a strong acid must be able to dissociate completely into ions in water. For example, hydrogen chloride dissociates into hydrogen ion and chloride ion. In water, hydrogen ion combine with water to form hydrogen ion. In water, there's no hydrogen chloride molecule exist because 100% of the molecule dissociate becomes ions, chloride ion and hydrogen ion. And that is an example of strong acid. A weak acid, on the other hand, only dissociates slightly to form ions in water. For example, acetic acid, CH3COOH, it only dissociates 5% of CH3COO negative, so only 5%, all right, with hydrogen ion. 95% of the molecules, stay in the solution unreacted. So in dilute solution of weak acid, most of the acid molecule are undissociated. As we know, most reaction has an equilibrium, and the equilibrium constant tells you is a measure of the reaction extent. So for this acid reaction, react with water dissociation reaction, in this case, the K constant is the product divided by reactants. So product is the hydrogen ion and the anion divided by unreacted acid molecule and water. So a weak acid means only small amount of the hydrogen ion and the anion is generated, and most molecules unreacted, and that gives you a small Kc. A weak acid means a small K constant of the dissociation reaction. This diagram shows the extent of dissociation for strong acids. Before the acid is dissolved in water, and this is the relative number of acids, HA. After it dissolved in water, HA is gone. There's no acid left. Instead, you have anion, you have hydronium ion. At the molecular level in this diagram, you cannot find HA molecule. Instead, you find hydronium ion, you find anion. This diagram shows the extent of dissociation for weak acids. So before the acid is dissolved in water, and that's the relative number of molecules of the acid, okay, of the weak acid. After it dissolves in water, you can see almost all of them remain unreacted. There's only a small amount of hydronium ion generated, plus the anion. At the molecular level, you can find a lot of acid molecules unreacted. There are a small amount of hydronium ion and anion in the solution. When a metal such as zinc is placed inside a strong acid, a lot of bubbles coming out. These bubbles is the hydrogen gas generated by the reaction between acid and the metal. For a weak acid, on the other hand, there's only a very small amount of bubble you can see. And this is because strong acid 100% dissociate into hydronium ion and anion. In a weak acid solution, very small amount of hydronium ion is generated. And this it's this hydronium ion that react with zinc or the metal to give hydrogen gas. As we have shown before, for this acid dissociation reaction, there is a equilibrium constant Kc, which measures the extent of reaction, also tells you the strength of the acid, because Kc is the product divided by reactants. The product is the hydronium ion and the anion generated by this dissociation reaction. A strong acid means it generates a lot of hydronium ion, so large product, small reactants concentration, that give you a large Kc. So strong acid, a larger Kc. A weak acid, a small Kc. Now in this equation, there's a water concentration here, which is a constant that doesn't change from solution to another solution. So if we compare different acid solution, and the concentration of water is the same, which doesn't help the comparison. And therefore, if we can remove this one, then we can define another constant, which is called acid constant. So here is the acid constant, and you can see acid constant is almost the same as equilibrium constant, but we just removed the water concentration. And because water concentration is a constant, so the comparison is still valid. It's the same. For example, if we compare 6 and 2, we know 6 is greater than 2. But if we divide by a constant, for example, we divide by 2 on both sides, then it's 3, 1. So 3 is still greater than 1. So by removing this water concentration, Ka is still almost same as Kc, that measures the strength of the acid. Okay, so a strong acid give you high concentration of the hydronium ion, which give you a large equilibrium constant and a larger Ka. So strong acid, large Ka. A weak acid, a small amount of dissociation, so small hydronium ion give you a smaller Ka. So Ka is comparable with Kc and the strength of the acid. Okay, strong acid, large Ka, weak acid, smaller Ka. Okay, so the value of Ka is an indication of acid strength. Okay, when you think about the Ka, okay, you can think about almost the same as the equilibrium constant of this dissociation reaction. This table shows Ka values for some monoprotic acids. From this table, you can say chlorous acid is a stronger acid than acetic acid. How do you know? When we look at the Ka, for chlorous acid, the Ka is 1.1 times 10 to the minus 2. For acetic acid, 1.8 times 10 to the minus 5. 10 to the minus 2 means 0.01. 10 to the minus 5 means 0.00001. So this is a smaller number, and this is a larger number. A larger number means a stronger acid. Here I will show you a list of strong acids and weak acids. It is important that you spend time to memorize them. Strong acids include hydrohalic acids. Halic means halogen, so chlorine, bromine, iodine. Group 7 elements, the binary acids, are strong acids, excluding hydrofluoric. This is not a strong acid. Hydrochloric, hydrobromic, hydroiodic, these are strong acids. Remember these. Oxo acids, including nitric acid, sulfuric acid, perchloric acid. Okay, NO3 is nitrate, so HNO3 is nitric acid. SO4 sulfate, H2SO4 is sulfuric acid. ClO4 is perchlorate, so HClO4 is perchloric acid. Okay, so remember these are strong oxo acids. Now, if you remember all this, then if you see other acids, most of the time they are weak acids. So how do you make sure? Here is a rule. If the oxygen atom exceeds the number of ionizable protons by 2 or more, then they are weak acids. Okay, let's count here nitric acid. 3 oxygen minus 1 hydrogen, that's equals 2. Sulfuric acid, 4 minus hydrogen equals 2. In perchloric acid, 4 oxygen minus 1 hydrogen equals 3. So they all are greater than 2 or more. So they are strong acids. Okay, so again, remember this one, the 7 group 7, and the oxo acids, 3 of them. Okay, they are very strong acids. Weak acids include, of course, hydrofluoric acid. All right, that's excluded from strong acid in group 7. Acids in which hydrogen is not bonded to oxygen or halogen. So cyanide, okay, hydrogen cyanide. This is a weak acid because hydrogen attached to carbon. Okay, so that's a weak acid. Oxo acids, all right, so excluding those. So the rule is the number of oxygen atoms exceeds or equals the number of ionization protons by only 1. Okay, only 1. So for example, this one, oxygen 1, hydrogen 1 equals 0. Okay, oxygen 2 minus 1 equals 1. All right, so oxygen is equal or less. Okay, equal or more than proton by 1. Okay, and those are weak acids. So again, it's important that you memorize those. It will helpful a lot. Next is organic acids. Organic acids has the formula RCOOH. Whenever you see COOH, that's a organic acid. So organic acid can attach to a different R group. For example, CH3, COOH, C6H5, COOH, or C2H5, COOH. Whenever you see this group, organic acids, they are weak acids. Okay, so these are weak acids, and these are strong acids. Strong bases include water-soluble compounds containing hydroxide and oxide. In other words, ionic compound which the anion is hydroxide or oxide, the cation must be group 1 metals, lithium, sodium, potassium, rubidium, cesium. These are group 1 metals. Or group 2 metals, okay, group 2 metals, excluding beryllium and magnesium. Okay, for example, sodium hydroxide. Okay, it's a ionic compound. Anion is hydroxide. Cation is group 1, okay, metal, or calcium hydroxide. Okay, hydroxide with group 2 metal. All right, group 2 metals. So these are strong bases. Now weak bases. Okay, if you see a nitrogen containing compound that has a lone pair electron, they are weak bases. So nitrogen with 3 hydrogen, this is amine, ammonia. So ammonia is a weak base. Or organic, okay, amines, for example, CH3 and H2. Okay, that's a weak base. Sample problem 18.1. Classify each of following compounds as a strong acid, weak acid, strong base, or weak base. Okay, A, potassium hydroxide. So it's an ionic compound with anion hydroxide, cation potassium, group 1 metal, must be a strong base. Okay, group 1 metal, hydroxide is a strong base. In B, we see COOH. We know it's organic base, organic acid. So this is organic group. Okay, so organic acid usually it's a weak acid. Okay. In C, H2SeO4. Se is selenium, which is a group 6 element. Okay, this reminds us sulfur. So we know H2SO4 is called sulfuric acid, is in the list of strong acid. So the same group selenium should also be a strong acid. Another way to look at it is to count oxygen and hydrogen. The difference is 4 minus 2 equals 2. Okay, if the difference is 2 or more, that's a strong acid. Okay, in D, we see nitrogen, and that reminds us, okay, with lone pair electron, even though it doesn't draw it. If you draw Lewis dot structure, it is a lone pair electron. So that indicates this is a weak base. Water molecules undergo auto-ionization or self-ionization reactions, in which 2 water molecules combine forms a hydronium ion and a hydroxide ion. In this diagram, we show a water molecule use its lone pair electron to take a proton away from a neighboring water molecule to form a hydronium ion, and the other molecule forms a hydroxide. Now this reaction takes place in all water containing solution, even in pure water. Although the extent of this reaction is extremely small, only very tiny amount of water ionize to form hydronium ion hydroxide. This reaction plays an important role in controlling acidity of an aqueous solution. This auto-ionization reaction has an extremely small equilibrium constant, which equals the product hydronium ion, hydroxide ion divided by water concentration to the second power, because you have a 2, coefficient 2 here. Now in this equation, water concentration is a constant. If we multiply by water concentration squared on both sides, okay, water concentration cancel each other on the right side. On the left side, this product gives you a new constant because both water concentration and the Kc are constant. And so this gives you a new constant which equals 10 to the minus 14, a very small number. And the right side is a product of the hydronium ion concentration and hydroxide ion concentration. Both are ions, and this constant has a name called ion product constant, Kw. Okay, so now we have an equation. The product of hydronium ion, hydroxide ion equals Kw, the ion product constant, which equals 10 to the minus 14. If water is pure, then it will generate equal amount of hydronium and hydroxide. So the concentration of hydronium ion, hydroxide ion should be square root of Kw, 10 to the minus 7. So in pure water, hydronium ion equals hydroxide ion equals 10 to the minus 7, a very small amount of hydronium ion, hydroxide ion. Now, if water is not pure, then these two concentrations may not be equal. So one may be more than the other, and that determines whether the aqueous solution is acidic or basic. Since the product of hydronium ion and hydroxide ion is a constant, a change in hydronium ion causes an inverse change of hydroxide. For example, 2 times 10 equals 20. If 2 becomes 4, okay, increase, then 10 must decrease to 5. So 4 times 5 is still 20. Increase 1, decrease another one. Okay, and so in aqueous solution, if hydronium ion is high, hydroxide must low because the product is a constant. Conversely, if hydroxide is high, hydronium concentration must be low. Okay, we can define acidic or basic in terms of the relative concentrations of hydronium ion and hydroxide ion. If hydronium ion concentration is greater than hydroxide, it's acidic. If hydroxide concentration is greater than hydronium ion, it's basic. In pure water, they are equal, and that is a neutral solution. This again shows the relationship between hydronium ion and hydroxide ion and the relative acidity of solution. In pure water, hydronium ion equals hydroxide ion. It's a neutral solution. When hydronium ion is greater than hydroxide ion, it's acidic solution. When hydroxide ion is greater than hydronium ion, it's a basic solution. In any event, the product of the hydronium ion, hydroxide ion is a constant, 10 to the minus 14. Sample problem 18.2. A research chemist adds a measured amount of hydrogen chloride gas to pure water at 25 Celsius and obtains a solution with hydronium ion this amount. Calculate hydroxide concentration. Is the solution neutral, acidic, or basic? Now, without calculation, you may be able to predict that it is acidic because hydrogen chloride is an acid. When acid is added to water, it should be acidic. But let's calculate hydroxide concentration and compare with hydronium ion. Okay, so to do that, first we look at knowns and unknowns. The known is we have hydronium ion concentration is here. We also note Kw. Don't forget ion constant. All right. So we know the important equation is hydronium ion concentration multiplied by hydroxide concentration equals Kw. Okay, so Kw is known, hydronium concentration is given, hydroxide can be calculated. So hydroxide should be Kw divided by, so this goes here, divided by hydronium ion. Okay, and therefore the solution is Kw divided by hydronium ion and plug in. Okay, Kw is 10 to the minus 14. Hydronium ion 3 times 10 to the minus 4, and that gives you 3.3 times 10 to the minus 11, and that is much smaller than the hydronium ion given, and therefore it is acidic solution. More hydronium ion is an acidic solution. In aqueous solution, the hydronium concentration or hydroxide concentration can change in a large range. For example, in pure water, the hydronium ion is 10 to the minus 7. Okay, as we already know, this is pure water. And in acidic condition, let's say here you have acidic condition, and the hydronium ion may be 10 to the minus 2. Okay, this is because hydronium ion hydroxide ion product is always 10 to the minus 14. So if hydronium ion is 10 to the minus 2, then hydroxide will be 10 to the minus 12. So the product, these two product, is 10 to the minus 14. And 10 to the minus 2 is greater than 10 to the minus 12. So it is acidic because you have more hydronium ion than hydroxide. And you can see the concentration of hydronium ion in neutral water is 10 to the minus 7. In acidic, it can be 10 to the minus 2 or minus 1, so it changes a lot. Okay, large range is inconvenient. So we define pH, okay, to make this easier. So the pH is defined as negative log concentration of hydronium ion. So let's apply to pure water first. So pH in pure water should be negative log of hydronium ion, which is 10 to the minus 7. And if you use a calculator, log 10 to the minus 7 is just negative 7. And you have a negative sign here, and that makes it 7. Okay, so pure water has a pH 7, and that is much easier than 10 to the minus 7. Okay, what about acid solution? Okay, let's calculate pH. So negative log 10 to the minus 2, for example. Okay, if you use a calculator, log 10 to the minus 2 is just a negative 2. And you have a negative sign that gives you just 2. So pH value for this solution as acid solution is 2. And also you see 2 is smaller than 7. So that means acid solution has a pH value smaller than 7. Pure water has a pH value 7. And if you do another example for basic solution, the pH value is greater than 7. Okay, greater than 7 for basic solution. All right, so here is the conclusion. In acidic solution, pH is smaller than 7. In neutral solution like pure water, pH equals 7. In basic solution, pH is greater than 7. Okay, the more concentration of hydronium ion here, the smaller the pH, okay, the more acidic. So here shows you some typical acid base with their pH. Hydrogen chloride is a strong acid. The pH can be close to 0, very small. Smaller pH, more hydronium concentration, and more acidic. All right, and lemon juice is about 2.5. Vinegar is here about 3. And neutral water is 7. Seawater is weakly basic, and detergent solution usually pH 10, so greater than 7 is the basic, and household ammonia is about 12. Sodium hydroxide is a very strong base, pH is close to 14. We already know how to use Ka, the acid constant, to predict the strength of an acid. Okay, the larger Ka give you a stronger acid. Okay, this is because Ka is similar to the equilibrium constant for the dissociation reaction of an acid. So the larger Ka means more acid dissociated becomes hydronium ion. Okay, so for example, in this table, hydrogen sulfate is a stronger acid than phenol because the Ka is 10 to the minus 2 is greater than 10 to the minus 10. Okay, now if you compare the Ka of these acids, you will see they vary in a large range, okay, large range, 10 to the minus 10, 10 to the minus 2. So it's inconvenient to use these numbers. And similar to the idea of pH, we define pKa. So pKa is defined as negative log Ka, just like pH equals, so pH equals negative log hydronium ion. Okay, the advantage of using log is that if you have a number is 10 to the nth power, this just equals to n, so make it simpler. Okay, now note that also we have a negative sign. So if a negative sign, if you calculate, you will find that a large Ka give you a smaller pKa. Okay, so you see this is 1.99, but this is 10, which corresponds a smaller Ka. So smaller Ka, a larger pKa. So this go opposite, and this is due to the negative sign. Ka goes in increase up, and the pKa goes down. Okay, they are opposite. So if you are looking for a strong acid, you look for a large Ka or a smaller pKa. All right. So a low small Ka, so small Ka is a small low pKa. So a low pKa is here, correspond a high Ka, large Ka here, which is a stronger acid. Okay, a weak acid. So this is a weak acid phenol, which has a low small Ka, a large pKa. As we already know, the product of hydronium ion, hydroxide ion is Kw, which is 10 to the minus 14. If we apply negative log on both sides, the right side becomes negative log Kw. The left side is the negative log, the product of two concentrations. One is hydronium ion, one is hydroxide ion. Now in math, if we have a log A times B, it can be separated into log A plus log B. So the left side, you have a negative sign, and therefore it can be written as negative log hydronium ion concentration minus log hydroxide concentration. Now the first one is the definition of pH. This is just the pH. And similarly, we can define the second one as pOH. Okay, so negative log OH is pOH. And the right side equation, negative log Kw, can be defined as pKw. So now we have this equation. pH is this one, pOH adds together give you pKw. Okay, so pKw. Now pKw is negative log 10 to the minus 14, which is just 14. And so it gives you 14. So pH plus pOH equals 14. Okay, so this equation, because right side is a constant, so left side, if you increase one, the other must decrease. If you increase pH value, pOH must decrease. So this is similar to this equation, where if you increase hydronium concentration, hydroxide concentration will decrease. And here, if you increase pH value, pOH will decrease. These are the two important equations we just learned. The product of hydronium ion, hydroxide ion concentration equals 10 to the minus 14, and the pH plus pOH equals 14. Okay, so in a neutral solution, the hydronium ion equals hydroxide concentration, which is 10 to the minus 7, and the pH and equals pOH, which equals 7. In acidic condition, hydronium ion is greater than hydroxide, and the pH is less than 7, pOH is greater than 7. In basic condition, the hydrogen concentration is smaller than hydroxide, and the pH is greater than 7, pOH is less than 7. Sample problem 18.3. Calculate hydrogen ion concentration, pH, hydroxide ion concentration, pOH for each of the following solution. A, 0.3 molarity nitric acid, and B, 0.0042 molarity of calcium hydroxide. So first thing you need to realize is that both acid and base are strong acid and strong base. They are strong acid, strong base. And this is very important because later you will see that calculation of strong acid, strong base is very different for weak compared with weak acid and weak base. For strong acid, so all acid will dissociate into ions, and therefore if we know the concentration of nitric acid, we know how much hydrogen ion can be generated, because all acid becomes hydrogen ion. Of course, hydrogen ion becomes hydrogen ion. So this all becomes hydrogen ion, which equals hydrogen ion. And therefore, for strong acid, as long as you know the concentration, you know the hydrogen ion concentration already, okay? Because they all dissociate. On the other hand, for a weak acid, and that will be different. So be careful with that later, okay? And with this high concentration, then you can calculate the pH, which is negative log of this concentration, give you pH, okay? And then how do you calculate the pOH concentration? Well, there are different ways. One way is hydrogen ion concentration, which we already found, times hydroxide equals negative, which equals 10 to the negative 14, right? kW. So we can calculate hydroxide. And then how do you calculate pOH? You can either use negative log OH, or you can use pH plus pOH equals 14. So there are several equations we can use, okay? So that's for A. Now for B, again, it's a strong base. Strong base means they all dissociate into calcium ion and hydroxide ion. Note that you have two hydroxide ion here. So whenever you have one more calcium hydroxide, you forms 2 moles, okay? And therefore, the concentration of hydroxide will be twice of this amount, okay? Now, again, this is only for strong acid base. So for strong base, you get hydroxide, okay? From this, you get hydroxide concentration. You need to times 2, okay? Because they dissociate into 2 of them. And with hydroxide, how do you calculate the pH? You must get hydrogen ion, because pH is defined as negative log hydrogen ion, not hydroxide. So you must calculate hydrogen ion. How do you do that? Okay, you can use this equation. Hydrogen ion hydroxide equals 10 to the minus 14. Okay, when you get hydrogen ion, then you get pH, okay, and then you get pOH. So let's look at A. This is the concentration of nitric acid, and because it's a strong acid, so all this concentration becomes hydrogen ion concentration. So that's the first important step. So you can see here why I ask you to memorize the list of strong acid. Because if it's strong acid, then this is the way to calculate. If it's weak acid, then we'll learn later a different way to do it, okay? And so with the hydrogen ion concentration, we calculate the pH, which according to definition is negative log hydrogen ion concentration. use your calculator, you get 0.52. Okay, next, to calculate OH, you need to use the equation, the product of OH and the hydrogen equals Kw. And so OH is Kw divided by hydrogen ion. Okay, so hydrogen ion is calculated, or is here. Okay, so put in, you get hydroxide, and then POH, according to the definition, is negative log OH, and that gives you 13.48. All right, so that's A. Again, it's for strong acid. All concentration of acid becomes hydrogen ion. If it's weak acid, okay, we'll show you we need a Ka later how to do it. Okay, more steps. Okay, now in B, again, this is a strong base. So how do you know it's strong base? Well, it's a hydroxide. It's a group 2. Remember, group 2 elements, metal with hydroxide are strong base. So this is strong base, and this all becomes hydroxide, but you need to times 2 because you have a 2 here. Okay, and therefore the hydroxide concentration is 0.0084. With hydroxide, you can calculate POH. Okay, how do you calculate pH? You need to know the hydrogen ion, and the hydrogen ion hydroxide ion product is Kw. So from this, you calculate hydrogen ion, and finally you calculate pH. So again, and this is for strong base. So all the concentration becomes hydroxide. If it's a weak base, we'll see later, okay, how to do that, more steps. So far, we have studied Arrhenius acid-base theory. In this theory, acid is a proton donor. Okay, in water solution should be hydrogen ion, but for simplicity, we can say it's just a proton donor. That's an acid. A base is a substance that contains hydroxide. And the reaction between acid base is between hydrogen ion and hydroxide ion. So the reaction is due to the hydroxide lone pair electron. Okay, you have oxygen has a lone pair electron, hydrogen has no electron. So what happens is lone pair electron goes between hydrogen and oxygen and forms a new oxygen-hydrogen bond. So this bond is due to this lone pair electron. Okay, so in that sense, we can say this hydroxide is a proton acceptor. Okay, so it's a CEPTOR. So hydroxide is a proton acceptor. To accept a proton forms water. Okay, and that's the base. Now, is there other anions that can accept proton? Okay, yes, and that's why in another theory called Bronsted-Lurey theory, okay, we define acid is still same as Arrhenius theory. That is, acid is a proton donor, but the base is not just hydroxide, but it says it's a proton acceptor. Any species that can accept proton, for example, nitrogen, NH3, has a lone pair electron, and therefore it can react with proton. This will form a bond between hydrogen and nitrogen. So ammonia is also a proton acceptor. So in Bronsted-Lurey theory, ammonia is also a base. Now this is not Arrhenius base, because Arrhenius base must have hydroxide. In Bronsted-Lurey theory, as long as it can accept proton, can react with proton, all right, then it is a base. So this theory includes Arrhenius theory. So hydroxide is also a Bronsted-Lurey base, okay? So because it can accept proton, but there are more, so it's wider. Using Bronsted-Lurey theory, Many reactions now can be considered as acid-base reaction. For example, when we dissolve hydrogen chloride, so this blue one is chlorine and this smaller ball is hydrogen. Okay, when you dissolve in water, okay, this is water molecule. The center one, red one, is oxygen with 2 hydrogen, and these 2 are lone pair electron. All right, the one of the lone pair electrons go between this hydrogen and oxygen, form a new bond. So this form a new bond, and the chlorine hydrogen bond break give you a hydronium ion. Okay, that's a hydronium ion and a chloride ion. Okay, so in this reaction, hydrogen chloride donate a proton to water, and that's an acid. Water accept proton from hydrogen chloride, and therefore it's a base. Okay, let's look at another reaction. Dissolve ammonia in water. So now water, oxygen has 2 lone pair electrons, but the nitrogen also have a lone pair electron, and the lone pair electron of the ammonia has a higher power, okay, to react than the lone pair electron of oxygen, and therefore it is this lone pair electron that goes between nitrogen and the proton, form a new bond, and that's the new bond. Okay, so ammonia becomes ammonium, okay, and the water becomes hydroxide. So in this reaction, water donate this proton to ammonia, and it's an acid. Ammonia accepts this proton from water, and it's a base. Let's look at another Bronsted-Lurey acid-base reaction. In the forward reaction, hydrogen sulfide forms a hydrogen sulfide ion by donating a proton to ammonia, and therefore it is an acid because it's acid, a proton donor. On the other hand, ammonia accepts the proton and forms ammonium ion. So ammonia is a base. Now the reverse reaction is the opposite. So in the reverse reaction, hydrogen sulfide ion, okay, accept a proton from ammonium ion to go back to hydrogen sulfide, and therefore in this reaction hydrogen sulfide is a base because it accepts proton, okay, and ammonium ion donate the proton to hydrogen sulfide ion, so it is an acid. Okay, so you can see we start with hydrogen sulfide as an acid. We end up with a hydrogen sulfide ion, which is a base. So these two are a acid-base pair, acid and a base, conjugate. So we call conjugate acid and the base pair. Okay, ammonia is a base in the reactant, and ammonium in the product as a acid. So again, these two are acid-base pair. So ammonia, ammonium. Okay, one is a base, one is an acid. So acid-base pair. Again, in this reaction, the hydrogen sulfide and hydrogen sulfide ion, these are conjugate acid base pair, and hydrogen sulfide is an acid and the hydrogen sulfide ion is a base. So hydrogen sulfide is a conjugate base of the acid hydrogen sulfide. Similarly, ammonium are conjugate acid base pair. Okay, and ammonium here is an acid. Okay, it's a conjugate acid of the base of ammonia. So in Bronsted-Lurey acid-base reaction, an acid and a base react to form a conjugate base and a conjugate acid. So this acid react with the base, acid forms a conjugate base forms a conjugate acid. And this shows that you have two pairs of conjugate acid base. So acid base 1, so that's a pair, acid base 2, pair, another pair. Here shows some examples of conjugate pairs in some acid-base reactions. In reaction 1, hydrogen fluoride donate proton to water to give fluoride ion and hydronium ion. And so because hydrogen fluoride donate a proton, it's an acid. And water accept the proton, so it's a base. Okay, on the reverse reaction, hydronium ion donate the proton to fluoride to go back to water. So this is an acid. So this is a conjugate acid of water. Okay, and the fluoride accept the proton, and therefore it's a conjugate base of hydrogen fluoride. So you can find similar way, you can find the acid-base pairs on reaction 1, 2, 3, 2, 3, 4, 5, 6. Simple problem 18.4. The following reactions are important environmental processes. Identify the conjugate acid-base pairs. Okay, so to find conjugate acid-base pairs, you need to find the species that donate hydrogen to be acid. The substance accept proton is a base. The acid after donate the proton becomes a conjugate base, and the base becomes a conjugate acid. So let's look at A. Okay, so in A, you can see that H2PO4 becomes HPO4 2-. So it donates a proton because the product has one proton missing, so it must donate a proton. And carbonate becomes bicarbonate, has one more hydrogen, so it's an acceptor, and therefore this is an acid, okay, because it donates a proton, and this is a base. And after donate the proton, and it becomes a conjugate base. So this acid becomes conjugate base, and the base becomes conjugate acid. And therefore we have two pairs. One is H2PO4, it's an acid, and the conjugate base is HPO4 2-. And the other pair is carbonate, is a base, and bicarbonate is a conjugate acid. In B, water becomes hydroxide. So water must donate a proton to SO3 2-, and therefore water is an acid, and the product is a conjugate base. SO3 2- must accept a proton to become a hydrogen SO3-. So this is a base, and that's a conjugate acid. So the conjugate acid-base pair are one is water and hydroxide. The other is SO3 2-, HSO3-. Many acid-base reactions are reversible. The net direction of acid-base reaction depends on the relative strength of the acids and the base involved. As we have seen, in an acid-base reaction, there are two pairs of conjugate acid and conjugate base. For example, in this reaction, hydrogen sulfide is an acid, and hydrogen sulfide ion is a conjugate base. Ammonia is a base, and ammonia is a conjugate acid. Okay, so you see you have two acids. This is acid 1, this is acid 2. Okay, and this is a base 1, and this is a base 2. The reaction always favor from stronger acid to weaker acid, stronger base to weaker base. Okay, so if reactants includes stronger acid, strong base, the product is weaker acid, weak base, and the forward reaction will be favored. Here shows the strength of conjugate acid-base pairs. As we already know, hydrogen chloride, sulfuric acid, nitric acid, these are very strong acids. The conjugate base, chloride, hydrogen sulfate ion, nitrate ion, these are very weak base. Okay, so strong acid, their conjugate base are very weak. On the other hand, water, let's see, water is a very weak acid, but the conjugate base, hydroxide, is very strong. Okay, so acid and their conjugate base are opposite. Okay, one is strong, the other must be weak. Sample problem 18.5. Predict the net direction and whether Kc is greater or less than 1 for each of following reactions. Note these reactions are all acid-base reaction, and as we know, acid-base reaction favors from stronger acid to weaker acid or stronger base to weak base. In order to know the direction, we need to identify conjugate acid-base pair, and then use the table, we know which one is stronger acid, which one is weaker acid. So in A, okay, so let's see A, and H2PO4, all right, donate the proton to ammonia to give HPO4, 2 minus, okay, because this has 2 hydrogen, this has 1 hydrogen, therefore this must donate a proton, so this is an acid. Okay, and this must be a base to accept the proton to become ammonium, and so this is a conjugate acid of ammonia, and this is a conjugate base. Okay, so let's compare these acids. This is acid 1 and this is acid 2. Okay, if you go back to the previous slides, and you will find that this one, H2PO4, is a stronger acid than ammonium, and which is a weaker acid. Okay, similarly, you can find ammonia is a stronger base than HPO4 2 minus, which is a weaker base. So the reaction goes from stronger acid to weaker acid, or from stronger base to weaker base. So the forward reaction is favored, and therefore K must be greater than 1. Now, if the reaction is disfavored, if the reverse reaction is favored, then K will be less than 1. If the reactants product are comparable, then K equals 1. In B, water forms hydroxide, so water must be a acid. Okay, it donates a proton, and hydrogen sulfide ion must be a base. Okay, and water becomes hydroxide, so hydroxide is a conjugate base, and hydrogen sulfide must be a conjugate acid of hydrogen sulfide ion. Okay, so we compare these two acids, acid 1, acid 2, and if you go back to the table, you will find water is a weaker acid, hydrogen sulfide is a stronger acid. So this reaction is go from weaker acid to stronger acid. The reaction is disfavored, and K must be less than 1. You already know how to solve problems involving strong acid, strong base. Solving problems involving weak acid is more complicated. Here are the steps. So we begin with a balanced equation and the K expression. Okay, we define X as the unknown change in the concentration that occurs during the reaction, and we will use the same skills we learned in the last chapter, all right, to construct reaction table in terms of X. And then sometimes we make assumptions. that simplify the calculation. Okay, then we construct values into the K expression and solve X. Okay, then check that the assumptions are justified. When solving problems involving weak acid, we use a bracket to represent molar concentrations. And we make some assumptions, and that is hydronium ion concentration from auto-ionization of water is negligible. And a weak acid has a small Ka, and its dissociation is negligible. That is, at equilibrium, the concentration of acid is approximately the initial concentration of the acid. Sample problem 18.7. This question is about phenyl acetic acid. The formula C6H5CH2COOH. Okay, remember COOH tells you it's an organic acid, and we can simplify the name as HPAC. Okay, now so we can ignore all those. So a study of this acid shows that pH of 0.12 molarity HPAC is 2.62. The question is, what is the Ka of this acid? Okay, so this is about a weak acid. Now, what if this acid is a strong acid? Okay, do you remember how to do it? Okay, if it's a strong acid, then if we know the concentration of the acid, then we know the hydronium ion, so H3O concentration. All right, why? Because strong acid, all molecules dissociate and becomes the hydronium ion 100%. That is the strong acid. However, if it's weak acid, then only part of it dissociate. So you don't know how much you have to calculate. Okay, and that's the difference. If we know, if it's a strong acid and we know the concentration, then we know hydronium ion, then we can calculate the pH, we can calculate hydroxide, we can calculate pOH, remember? Okay, now if it's weak acid, then you have to construct the table, and we have to use the balanced dissociation equation. That's the first step. Construct the table as we did in the last chapter, the reaction table. Assume X is the change, solve it, so it's more complicated. So let's see how we do it in this question. So first we need to write the balanced dissociation equation, and that is this acid add water, okay, becomes hydronium ion. That's the dissociation reaction. So this is acid, simplified formula. Add water becomes hydronium ion, and the anion, okay, this is the anion, okay, is the PAC minus. Okay, so any acid you can write that like this equation. For example, if it says weak acid can be simplified as HA. Okay, so this is acid, and the dissociation reaction you can write as water goes to hydronium ion. Okay, so this proton goes to water, forms hydronium ion. So what left is the anion. Okay, and that's the general form to write dissociation reaction for a weak acid. This is a weak acid. Now in this case, PAC, that's the anion. So you get PAC negative. Okay, and then you write Ka, which is a hydronium ion concentration times the anion divided by the acid concentration at equilibrium. Okay, next we need to construct the table. To construct the table, we first write the balanced reaction equation, and then the first row we write the initial concentration, so 0.12 molarity of the acid. So that's the initial concentration. Now what about initial hydronium ion? Well, you may think water itself, auto ionization, give you 10 to the minus 7 molarity concentration, right? It's always has autoionization. But this is so small, we assume it's 0, okay? So we'll justify this, but this is one assumption we mentioned, that hydronium ion from the water ionization is negligible, okay? And anion is also 0 because at the beginning we only have acid, okay? So that's the first row, all right? Now this is the same as we did in the last chapter, so please go over the skills to write this table, okay? Next, what's the next row? The next row is the change, and so we assume the acid change is X because it's consumed, so we put a negative sign, and it generates X amount of hydronium ion, X amount of anion. Okay, what's the next? Equilibrium. So at equilibrium, and the acid, okay, still have 0.12 minus X left. So this is, okay, at equilibrium, how many acid still at present, okay? So you use initial minus change, and the hydronium ion is 0 plus X, okay? That's at equilibrium, how many hydronium ion in the solution, and the anion. Okay, next step is to solve it. Okay, how do we solve it? We look at the question to find information. It says the pH is 2.62, and this should be the information we use to solve it. Now, if we know pH, so what can we do? We know pH is negative log hydronium ion concentration. Okay, so if we know pH, we can solve hydronium ion concentration. And this is the hydronium concentration from the table. And therefore, let these two equal, and we can solve X. But first, let's solve hydronium ion concentration. So pH is 2.62, and therefore, hydronium ion concentration should be the anti-log, okay? Because pH is the negative log, so this is negative pH. Okay, so use your calculator, use anti-log of this one. You should get 2.4 times 10 to the minus 3 molarity. Okay, so that's the pH from, that's the hydronium ion concentration calculated from the pH value given. Now the table tells us this should equal to X. Okay, and so we can let X equals to this one. All right, and also note that the concentration is 10 to the minus 3, which is much greater than 10 to the minus 7, which is from autoionization from water. So our assumption is justified because autoionization is so small compared to our calculated hydronium ion concentration. It's negligible. Okay, so X equals hydronium ion concentration. So now we have X. So what's the next step? We put back into this table to find all the equilibrium concentration. Okay, so we find the acid at equilibrium, and we find anion, which is just X. Okay, now we are ready to calculate Ka. Ka is the product divided by reactants at equilibrium. So this is X, calculate X divided by acid at equilibrium. Put back into equation, we can calculate 4.8 times 10 to the negative 5. That's the acid constant for this weak acid. As a last step, we need to justify our assumptions and calculate the percent errors. Okay, one assumption we made is the water ionization, which 10 to the minus 7 is negligible compared to the calculated concentration of hydronium ion. So we need to use 10 to the minus 7 divided by X, which calculate is this one, to see the percent. If percent is less than 5, then justified. The other one assumption is the concentration of acid at equilibrium is initial minus X, which is approximately just the initial concentration because X is very small compared to 0.112. But at the last step, we need to justify by using the X divided by 0.12 to see if this is very small, 5%. Okay. So here is the calculation. First, water flown, the hydronium ion flown water autoionization. So that's the flown autoionization divided by the hydronium ion calculated, which is very small, and so much smaller than 5%. So justified. Next is the X divided by initial concentration, which is 2%, and therefore it's justified. Sample problem 18.8. Propanoic acid, CH3CH2COOH, so it's an organic acid. We can simplify as HPr. So remember the general form for acid, we can write HA. So A in this case is Pr. And so it's a carboxylic acid whose salt are used to retard mold growth in food. The question is, what is the hydronium concentration of 0.12 molarity with Ka equals 1.3 times 10 to the minus 5? Okay, so compared to sample problem 18.7, both cases we have the initial concentration of the acid, of the weak acid. In the 18.7, we know pH, all right, and then we solve using pH, we solve hydronium ion, we calculate X, and then we can calculate Ka. In this case, Ka is given, okay, and then we want to find hydronium ion concentration. Okay, so even though conditions are different, ideas are the same. We construct the table, reaction table. Okay, first we write balanced equation, and then construct table, assume changes X, solve X. Okay, so idea is the same. So let's first write equation. Okay, the equation, this association equation is the same: acid, add water, hydronium ion, and the anion. Okay, so always the same, the dissociation reaction. Ka is the product divided by reactants. Okay, so next let's draw the reaction table. To construct the reaction table, we first write a balanced equation. So here is the balanced equation, and then initial concentration. So acid given 0.10, hydronium ion. Again, we assume hydronium ion flown autoionization of water is negligible. So write 0 here, and anion 0 here, that's initial. And next is the change. So change for acid is negative X, hydronium ion is positive X, anion positive X. And next, equilibrium. So equilibrium concentration for acid is 0.1 initial minus X. Okay, at equilibrium, hydronium ion is just X and the anion X. Okay, so next, solve X. How do we do that? Well, go back to the question. In this case, we know Ka. So we need to write the equation of Ka to calculate X. Okay, so last question, we know pH, hydronium ion. So let X equals hydronium ion, and we already solved X. But this case, we have to write X squared, okay, because this is X, so product divided by reactants, this one, that's the Ka. So this equals Ka, which is 1.3 times 10 to the minus 5, right? So we write the equation for Ka, product divided by reactants. X is unknown, so we can solve it. Now, if you look at this equation, this will give you a quadratic equation. Okay, is there a way we can simplify it? Well, if X is very small compared to 0.1, then we can omit x. Remember, that's one of the assumption we can make. So we assume, okay, Ka is small, so x is also small. If it's a weak acid, okay, weak acid Ka is small, that means only very small amount of acid dissociate give you a small x. So if small x, then we can say, oh, the denominator is just approximate 0.1. Okay, so assume x is very small, and then this, so that make the equation much simpler. So the equation, note the equation now is x squared divided by 0.1 equals 1.3 times 10 to the minus 5. And that make calculation much simpler, because now x squared is just 1.3 times 10 to the minus 5 times 0.1. Okay, and then x just the square root of everything. So here we can say x is the initial concentration, that's 0.1 is the initial concentration of the acid multiplied by Ka. This is the Ka. Okay, so initial concentration times Ka. Okay, plug in the data. All right, give you 1.1 times 10 to the minus 3 molarity hydronium ion. In this problem, we have derived a very interesting and useful equation, and that is the hydronium ion concentration at equilibrium for a weak acid. So X is the change, also the hydronium ion concentration, equals square root of the acid concentration, that's the initial acid concentration, multiplied by Ka. Okay, so that's a very interesting equation and also useful equation to remember. Now let's compare with a strong acid. If this is a strong acid, then the concentration equal to the hydronium ion. You don't need to calculate because 100% goes to hydronium ion, and so from there we can calculate pH, pOH, everything. But if it's a weak acid, then this is not equal. You need another information. If we know Ka and the initial concentration, then for a weak acid, the hydronium ion concentration can be calculated to be square root the initial concentration. In general, this is the initial concentration of acid times Ka. Okay, so if we know initial concentration of weak acid and Ka of weak acid, then we can also calculate hydronium ion concentration. Okay, so this equation is valid if X is very small and the condition is Ka is small. So that means this is valid for a very weak acid. Okay, so you need to check that. And you need to check the X is small, the error is less than 5%. In this case, if you calculate this divided by the initial concentration, you will find is 1.1% error, so which is justified. Okay, very small, negligible. Okay, again, remember this equation is very useful for a weak acid. How do you calculate the hydronium ion concentration?